Hello and welcome to the second module about treatment. In the last module, we looked at the different treatment stages as well as pre-treatment technologies. We are now moving further along the treatment process and have a look at primary treatment technologies as well as anaerobic technologies as a whole. We saw already what primary treatment is. Primary treatment is a separation of the settleable solids from the liquid part. You learned about anaerobic processes in module 2.7, presented by Lukas Ulrich. Anaerobic means processes that happen without the presence of oxygen. Anaerobic means literally no air. Anaerobic bacteria live in the absence of oxygen and transform the organic matter into carbon dioxide, or CO2, and methane, or CH4, also called biogas. Anaerobic processes are used both in primary and secondary treatment technologies. They are very efficient, especially in warm climates. Sometimes smelly, but exciting, isn't it? Let's start with the primary treatment technologies. Don't forget that for each technology that I will present, you will find more information here in the compendium. For example, the settler. The settler is the classical primary treatment technology. It is designed to remove suspended solids by sedimentation. The low flow velocity in the settler allows settleable particles to sink to the bottom, while the lighter constituent will float to the surface, forming the scum. The outlet is placed between these two layers in order to collect the settled effluent. A settler may be also called a sedimentation or settling tank, or in conventional treatment plants, a clarifier. Settlers can achieve an initial reduction of up to 50 to 70% of suspended solids and up to 20 to 40% of organic material. Settlers can be independent units or merged into other technologies, like in the septic tank that you saw before and others that we will see later. The performance of settlers can be enhanced by including inclined plates, called lamella, or tubes, or with the use of chemical coagulants. Let's now have a look at the Imhoff Tank. The Imhoff Tank is a primary treatment technology that combines solid-liquid separation and digestion of the settled sludge. Because there is sludge digestion, there is production of biogas, whose bubbles may disturb the settling process. For this reason, the flow tank, or settling compartment, is designed with a V-shape, which prevents gas bubbles to come up and force them to the sides, as well as the scum. Depending on the design and conditions, the Imhoff tank may have the advantage to lead to good sludge stabilization, which is not the case with a standard settler. So, to sum up, the advantage of the Imhoff tank over a standard settler is the production of a more stabilized sludge, easier to treat. The sludge removal frequency is also much lower. On the other hand, it is a more complicated system to build, it is quite a high or deep infrastructure, and consequently also more expensive. That's it so far for the purely primary treatment technologies. Let's look now at anaerobic technologies, which also fulfill secondary treatment functions. I nominated the ABR, or Anaerobic Baffled Reactor, and the Anaerobic Filter. You may already have heard about them in the module 2.7, as they can also function as a collection, storage, and treatment system at building or neighborhood level. Now we will consider them as proper treatment units. Same thing for the biogas reactor. It was presented in module 2.7 by Lukas Ulrich. Please refer to that module to learn more about it. Let's talk about ABRs. An ABR is a kind of improved septic tank with a series of baffles under which the wastewater is forced to flow. The baffles can be replaced by tubes, as shown here, which is a hydraulic design improvement. The settler can be integrated to the ABR or separate. The wastewater is forced to flow through the sludge, which is a thriving active biomass. The anaerobic bacteria present in the sludge degrade part of the suspended matter present in the wastewater passing through it. Usually, ABR counts between 3 and 6 upflow chambers. Upflow because the water flows from the bottom to the top of each compartment. The tanks should be vented to allow for controlled release of the gases. In an ABR, the hydraulic retention time is between 48 and 72 hours. ABRs can be very efficient to remove organic matter, with a reduction up to 90%. The ABR presents many positive aspects for low and middle income areas. It has low operation and maintenance costs, no electrical energy is required, and it is resistant to organic and hydraulic shock loads. As for the sludge, the retention time is long, from 6 months to several years. It is thus well stabilized and hence easier to treat further, and the sludging is not required frequently. An ABR is quite compact, as shown here in Egypt. What is more, they can be built underground, which gives flexibility for their implementation. They can even be implemented under a garden or a parking space. However, if the ABR looks simple, one should not forget that, as all the treatment systems presented here, it relies on biological processes. It is like a living organism. The startup period is crucial to reach an optimal performance and requires expert follow-up, at least for the first 6 months. The ABR is particularly appropriate for small-scale, or sometimes called decentralized wastewater treatment plants. It is important to mention here 2 opportunities linked with such systems: modularity and prefabrication. Modularity, such as represented in this figure from the German organization Borda, provides much more flexibility and allows to build treatment plants much closer to the needs, with the possibility to add further modules as the population grows. The prefabrication of treatment units allows for a much better quality control, and materials withstand better anaerobic wastewater. It also dramatically reduces the construction time. Such units can be locally manufactured, such as here in Indonesia. Let's close this parenthesis and go back to our technologies. Usually, the effluent from an ABR needs further treatment. To improve its effluent quality, a few compartments packed with filter media can be added. These are known as an anaerobic filter. Anaerobic filters can also be built immediately after the settler, as shown in this figure. It works exactly on the same principle as the ABR, with the addition of filter media, like gravel, crushed rocks, cinder, pumice, or plastic chips. Typical filter material sizes range from 12 to 55 millimeters in diameter. The ideal filter should have a large surface area for the bacteria to grow, with pores large enough to prevent clogging. As in the ABR, the water flows from the bottom to the top of the compartments, and a vent is installed on the top. The water level should cover at least 0.3 meters to guarantee an even flow. The filter is supported by a grid, so no as to clog the bottom of the compartment. The hydraulic retention time is the most important design parameter influencing the filter performance. A hydraulic retention time of 12 to 36 hours is recommended. Clogging is the main threat in an anaerobic filter. When the efficiency decreases, the filter must be cleaned. This is done by running the system in the reverse mode, or if you prefer, backwashing, or by removing and cleaning the filter material. This being difficult, it is better to avoid clogging as much as possible. The picture here shows 4 parallel ABRs and anaerobic filters under construction in India for a design capacity of 150 cubic meters, which is equivalent to about 1,500 inhabitants. Let's now have a look at a more sophisticated anaerobic technology, the Upflow Anaerobic Sludge Blanket Reactor, or USB. The USB is a single tank process. Wastewater enters the reactor from the bottom and flows upwards. A suspended sludge blanket filters and treats the wastewater as it flows through it. The sludge blanket is comprised of small agglomerations of microorganisms with a diameter of about 1 to 3 millimeters, which, because of their weight, resist being washed out in the upflow. Basically, the crucial point here is to maintain this equilibrium so that the sludge blanket does not settle but is not washed out either. That's what makes it a sensitive system. An upflow velocity of 0.7 to 1 meter per hour must be maintained. During the digestion process, biogas is produced and goes up. Critical elements for the design of a USB reactor are the influent distribution system, the gas-solid separator, and the effluent withdrawal design. The USB allows a high reduction of BOD, can withstand high organic loads, and leads to a low sludge production. It requests high-strength wastewater and so is often used for industrial wastewater. However, for it to run properly, it needs skilled operators and a constant wastewater supply and electricity. Developing the granulate sludge may take several months, so expert follow-up during the startup period is very important. To sum up, we can say that anaerobic systems are among the most efficient and compact. They work at best in warmer climates, so are particularly appropriate for tropical areas. What is more, anaerobic baffled reactors and filters require very little operation and maintenance. However, if they are very performant at removing organic matter, they remove little pathogen and nutrients. Thus, the effluent and the sludge need further treatment. In the next module, we will review the different aerobic treatment technologies. See you then!